Okay guys, this is the review of the exam 3 solutions that you all have either seen your grades or picked up your exams from my office. I will bring them on the exam number 4 so that you can have them for your records. This front page that you're seeing here is not just for is not unimportant. These things that I wrote there in bold are required, and not because I want to have an opportunity to take points off, but because I'm trying to force you to do what I know will make you solve your problems better. Okay? And I see that people who don't do it definitely do not manage to figure it out, because this is not simple, it's not high school anymore. And so I'm hoping that you're really going to take it seriously and start doing it on exam 4 and be really ready for the finals. Okay? So let's see our first problem. It's the problem we've solved about 600 times with all the explanations. So I'm not quite sure why this was not the gimme. I was thinking I'm giving you 20 points right off the bat, and it didn't happen. Okay, so let's go over it again. So we have this lap joint, and we have a single bolt, and the bolt is 10 millimeter diameter. And both the bolt and the plates are made with the same material. So I really made it simple for you guys. Okay, with allowable tensile stress. Let me pick a pen here. I got the new palette. I'm going to use yellow-green. Allowable tensile stress of 50 megapascals and allowable shear stress, okay, of 30 megapascals. And the load P is applied along the longitudinal axis of the joint as shown. So that means that the plates are loaded in tension, but the bolt is loaded in shear. It's as simple as it can be, okay? And so let's read the first problem. These two problems, the A and B, are unrelated. One is one case of one failure mode, the other one is the other failure mode. So I've given you the same problem, but two failure modes, and you have to do simple calculation for each to see, what you get. So the first one, calculate the largest load P that can be applied on the joint if we assume failure of plate in tension. So what is it the first thing you want to do here? You want to immediately copy this allowable tensile stress of 50 megapascals, because this is what relates to that problem. And then it says due to stress concentration, okay? And use the graph on the next page. So on the next page, you even have a graph drawn. And I've had people draw incredible things, including shear and torsion, but they had the graph that they had to just copy and paste from the previous page. Okay, so that was really surprising. So let's start solving this problem. Before we go there, let's look at that graph on the next page that deals exclusively with the stress concentration. You've seen it before. You have a plate. This is how it fails in stress concentration. You will have some normal loading, right, and your hole. And this is the case. So you know what you're supposed to do. You're supposed to calculate 2R over W, where 2R is the diameter of the hole, and W is the cross-section of it's the width of the part. And that's it. And once you find that number, you can find what the stress concentration is, okay? But this is your free body diagram, except for one thing. We need to find, and I'm going back now, we need to find at which cross-section we are looking at this, because we need to draw a free body diagram, okay? That's the important bit. And so let's start working on it. I'm going to choose a brown pen, okay? And this is what I would do. First, I would say that my sigma, as we said, let's first write it, the allowable tensile stress, and I'm writing it as sigma because it's normal. As soon as you hear the word tensile, that means normal, right? And that's equal to 50 megapascal. And then I'm going to draw a free body diagram for this problem, which looks like this. It's going to be that same plate we saw on this diagram. So one of these plates will fail in tension because they're the same. Either one we pick is going to be okay. So I'm going to pick this one here. And I'm going to cut it where? I'm going to cut it right where the hole is, right through the hole. to get this kind of diagram. Okay, and since I cut it right there, the left part doesn't exist. This is my force. I need to include the resultant on the left-hand side, right? And so I can either draw something like this, and from sum of x's, I will know that this is a p over 2 and p over 2, or I can decide to just do it like this, because it doesn't matter, right? It's basically acts on this surface here that's covered by this line. So whichever way you want to call it, you have P on the left and P on the right. That's all there is to it, okay? And we know that this width here is 50. I'm going to draw it here. And we know that the whole diameter is 2r, and that's equal to what? To 10 millimeters. Okay? And so the rest is easy. The first step is to find 2r over w, and that's equal to 2r is 10 millimeters, so it's 10 times a millimeter is 10 to the minus third meter, over w, which is 50 millimeters. So it's 50 times 10 to the minus third. We didn't even have to do that. We could have just done it in millimeters because we're dividing same units. So we basically have 10 over 50, which is equal to 0.2. Okay? And when you take that and find the location on the diagram, I'm going to do that like this and send you here. There's my diagram. I'm going to find 0.2 down there. Okay. I'm going to use a different pen. Let's say red. I'm going to find 0.2, go up until it intersects the curve. So that's my point. So I went in that direction. And then once I intersect the curve, I veer off to the right to look at what's the value there, okay, in that direction, to find my K. And we see that this point here is exactly between 2.5 and 2.6. So this is 2.5. Therefore, this one, which is between 2.4 and 2.5, must be 2.45. I was amazed how many of you could not even do the simple reading. It was perfectly clear. So to know how to read a point off a graph, that's very important. As an engineer, you have to be good at it, okay? So the value of our K is 2.45. So let's go back. Right here. And continue to work on a problem. 2.45, that was our problem, okay? So from there, we get K is equal to 2.45. And it's just a non-dimensional value, right? And we know that sigma allowed is equal to, that's the maximum one we're looking for, right? And we know that in stress concentration, sigma maximum is equal to K times sigma average. And we all know how to calculate sigma average. Our sigma max will be the sigma allowed, so the equation follows like this. 10, when you substitute all the values, you get 10 to the 10 times 6, 50 times 6 to, okay, 50 times 10 to the 6th power, that's a megapascal, is equal to K, which is 2.45, and then times, and what is our sigma average? It's the force versus the area. So the force is P, that's the P we're trying to find. And what would be the maximum average stress? It will be the maximum force over the smallest area that's available on that cross section. and the smallest area is right here. We can see it. It's this and that. It's not the entire width. So if you remember that this is a three-dimensional object, it will be looking like this. Okay? And so your surface area is this plus that. And these two, when you add them up, that's your surface that falls in here. So what is that equal to? It's equal to the surface area of the entire cross-section, which is 50 times the thickness, minus the surface area of the part that was lost when the hole was cut out, which depends on the diameter of the hole. So it's basically 50 minus diameter of the hole, and that's going to be equal to 50 minus diameter of the hole is 10, right? Times 10 to the minus third, because it's millimeters, and then times the thickness, which is 0.015. And when you calculate all this, I keep switching colors here so you don't get bored, you get that the P max is equal to 12.245 kilonewtons. Really, it's enough to just say 12.2 kilonewtons and that works, okay? So that's our maximum force P allowed in the case when we assume the failure of plate in tension. Okay, now let's solve the second problem. The second mode is failure of bolt by shear. The previous one was the failure of plate in tension. The second one is failure of bolt by shear. So now we forget about the both plates, we do the bolt, and which is what we've done, I think, about 3 times now, right? And I'm going to use the blue color. So let's look at how the bolt fails in shear. We have the two plates, if you look at them, they look like this. You've seen this many times. And the bolt is here, and it looks like that. And so what we do, it's not ready yet, right? I forgot to draw a force P and a force P. That's not a free body diagram. That's just a different view of our picture that I've shown up on top. And now what we're going to do, in order to mimic the failure of bolt by shear, we need to shear it off. So let's shear it off. It's this surface here that we cut horizontally. And now we have a proper free body diagram. I'm going to use a violet color. So the free body diagram looks like this. I'm going to keep the top. I don't know why I like the top, but I'm going to keep the top. You could keep the bottom if you prefer. It doesn't matter. And so I'm drawing the top part the same, and I'm even keeping the head of the bolt. But instead of the bolt shaft, there's just a little stump. And the entire bottom stuff is gone, doesn't exist anymore. And right on the stump, that's where the force is. So this was P, and I'm shearing this, and this is the internal shear force V. And when you do sum of x's equals to 0, you get that your V is equal to P. So wherever you have a V, you can switch it with P, right? And that is our internal force, is equal to this external force P. Our internal shear force V is equal to this external force P. And now you are armed with that, and with the fact that you know that your tau allowable is equal to 30 megapascals. Okay, now you can start solving this problem, which is literally a one-step problem. Okay, you know that your tau allow, that's the one you're going to equate with your maximum, because it's the maximum allowed, the maximum you can get out of this problem. And that's equal to the formula for the maximum shear, or for the average shear stress, would be V, and let me not do V, let me say P max. Actually, let me not do P max, let me say the V max, and we'll replace it. So I'm not going to skip steps, okay? So the formula for shear says that tau is equal to V over the surface area. The tau max would be V max over the surface area, which is what? The surface area of the bolt. And I'm going to write it here, bolt. Okay? the surface area of the bolt. That's all there is to it. And now we are going to substitute the values, okay? So the Vmax is our Pmax, right? And the A bolt is the area, surface area of the bolt, which is d over 2 square pi. That's it, okay? And the tau allowed is 30. So let's just write it up. The equation looks like this. 30 times 10 to the 6 pascals, right, is equal to Pmax. So instead of Vmax, we wrote Pmax. That's the one we tried to find. Divided by d half. So if our d of the bolt is equal to 10 millimeters, half of that is 5. So it's 5 square. So it's 25 millimeters square. And a millimeter is 10 to the minus 3 meters, and then squared, times pi. And you know how to sort this out. 10 to the minus third becomes 10 to the minus 6 when squared. You have a 25 and a pi and all these numbers. And so a minus 6 will become a 6 when it comes up. So it's basically these two will cancel. And you get the solution that says that P max is equal to, this is for failure of the bolt. Failure of the bolt by shear is equal to 2.356 kilonewtons. Okay? So now, that's this solution. And if you remember previously, it's on my other screen, but I don't want to bring it up. The P max for the previous one was equal to, there's only so much space on the screen, the way I made this letter bigger because I'm blind, remember? 12 point, and I need big letters, 12.245. That was the solution for the failure of plate in tension, and that was kilonewtons, okay? So these two numbers. And now the next question is, and actually I should probably repeat them. I'm going to use a new page and scooch this up a little. Based on the above results, if we apply load of P equals to 6 kilonewtons, what will be the mode of failure for this lap joint and why? Well, let me write here on the side for you the two values. So P for, that's the P max for plate failure is equal to 12.245 kilonewtons. And P max for failure of bolt in the shear, 2.356 kilonewtons. Okay, and so now you look at these two numbers. Okay, this is a 2. And what are we given? We are applying 6 kilonewtons. So we are applying 6 kilonewtons, and now you need to really compare 6 kilonewtons with these two numbers, and then make a decision. So what will be the mode of failure for this lap joint and why? And the correct result is, because 6 kilonewtons, okay, because 6 kilonewtons is greater than this number here, 2.356. It is greater than this number here, too, but it will reach the 2 first, right? It will never get to this number. So we know, because 6 kilo, this is all you were supposed to write here, because the 6 kilonewtons is greater than 2.356 kilonewtons, you will have a failure of bolt by shear if you apply that load. Very simple, okay? People wrote essays. It just amazes me. This is all the work, and I only copied this for you because I couldn't see, I don't have all that space. But you didn't even have to copy this. So it's just 2 lines, 4 points for nothing. And I don't know, I'm disappointed, okay? So this was the C, okay? So now let's go and solve the next problem. The next problem is this one. Talk about the gimme. All you had to do is recognize what these two pictures were associated with, the kind of loading and the kind of stress caused by that loading. Okay? And so that's very simple. This loading, as everybody knows, is torsion. You're twisting the rod around. And this is how we present the stress. Which stress? The shear stress. People wrote all kinds of names for stress. The only names we're talking about when we're talking about the kind of loading and the stress associated with it, we talk about torsion, axial, bending, and so on. And the stresses associated with them are either shear or normal, or axial, if you want to put it that way, but normal stress. Okay? And then in this case, when you have a constant distribution of stress, like this, the only case when you have that ever is axial loading, and the stress is normal. And so I did not have, I believe, a single one that was 100% correct on this one. I kind of had to give it some points because it was close. People were inventing their own words, but I don't think I had a single person who actually had it 100%. So you need to go through this, because this is going to be, if you leave this class with just understanding of this and ability to recognize all of them, or if I ask you, you have torsion, show me the shear stress distribution over the cross section, you have to sketch it like this, literally in a split second. Okay? There's no question about taking even time to think about it. All right? So that was the problem number 3. That was the problem number 2. I don't know how I ended up being problem number 3, because problem number 2 is on the other side. I never even noticed. Okay, so let's do that. Let's look at the next problem. Problem number 2 on the wrong page. You're designing a green non-mercury thermometer. And this is actually how thermometers are built, a simple one. There are other kinds too. You are counting on the thermal expansion of the metal rod BC. So that's the vertical one. That's the only one that's going to expand. And when it expands, it's going to push this whole arrow up because it's pinned here. So as it's pushing it up this way, there's also a pin. It's going to move that way. Okay. And what do we have given? We have the coefficient of thermal expansion. And we are told that this plastic pointer ABD, okay, which has a coefficient of thermal expansion 0. What does it mean? It's not affected by the change in temperature. This is the part of the problem you were supposed to recognize. Okay? So when you have a number like this, it is affected by the change of temperature. When you don't have a number, it is not affected by change of temperature. It's as simple as that. So there is no deformation due to temperature of this big arrow ABD. And you will calibrate the points from 10 to 60, okay? And you want the pointer to be in the horizontal position at 10. So this is all achieved in this picture. And also due to size constraints, we want this BC to be relatively small, just 50 millimeters. And the pointer angle at the 60 Celsius tick is this here. The key thing in this problem that you had to recognize is that this means it's a very, very, very small angle. The second thing you were supposed to notice that it's in radians. It requires no conversion of any any kind, because as we need radians to do all physical calculations. We don't do in degrees. And it's already in radians. So people who were going around doing calculations, happily punching numbers into the calculator, were wrong, wasting their time, okay? But the thing you needed to recognize about this is that this angle is very small. So the first thing I would have written here for my own records is theta is very small, which means that any kind of sine-based function, which is a tan or a sine, of theta will be approximately equal to theta. So tan or sine are approximately equal to theta. That's all you have to remember. Okay, and now we go further. So I'm going to start now a new page to get this off so that I can move this up a little and give myself some room. You're asked where on the pointer ABD should you fix the point B. So basically you're asked to calculate this distance here, AB, in order to satisfy all design requirements that I've just told you. And all connections are pinned, and the angle theta in the picture is vastly exaggerated. You should already know that, but I made sure to mention that. So let's just look at, I'm going to put it like this so I give myself some room to calculate. All right. So let's use, for example, a violet pen. What will be the first thing to calculate? I want to notice that my delta T is equal to the change in temperature, 60 degrees minus 10 degrees is equal to 50 degrees Celsius. Okay? And so now what we're going to calculate here is the following. I know that for that change in temperature, this bar CB will displace, maybe I should use a different pen here. I will use a red pen so that it sticks out. From here to there, that's how much the bar, this point B, will extend. The bar CB will expand. And that quantity is delta. I'm going to make it bigger here and write it as delta. I had incredible ideas people had in how they're going to write this. They decided to call this delta, that delta. It is not acceptable because this delta is used for specific things. And displacements are marked with a little Greek delta, which is exactly as I wrote it. So little Greek delta is equal to alpha times big Greek delta T times the length of this, original length of this bar, BC. And this is how it's denoted with a straight line on top, okay? And so let's substitute all the values. So that's equal to 20 times 10 to the minus 6, 1 over degrees Celsius, that's the alpha, okay, times delta T is 50 degrees Celsius, 50 degrees Celsius, so the degrees Celsius and degrees Celsius cancels, and then times 50, that's the BC, millimeters, which is 10 to the minus 3 meters. And from that you get that delta is equal to 5 times 10 to the minus 5 of what? This is in millimeters, so that's meters. This and these two cancel, so it's meters. Okay? So that's our delta. It's an intermediary result that now we need to use. And so the only thing that you had to recognize in this problem, in addition to the fact that delta is small, that we wrote up further up, is that now the geometry, right? And the geometry of this triangle AB, B prime. I'm going to call this point here B prime. And so even though I drew this pretty well, but let me draw this line here. This angle here we assume is a right angle. And so we have a right angle triangle A, B, B prime. We have the B prime, and we have this angle here, which is theta, right? That's this angle. So the length of this is completely irrelevant to us. We're not interested in that right now. Okay, we'll calculate that later. All we're looking at is this region here and what happens when this bar BC gets a little longer. That's all we're interested in. Right now, we're not interested in anything else. So let's see what we get out of this triangle A, B, B prime. The tan of theta is equal to what? The tan of theta is equal to this here, right? Which is what? The little delta divided by AB. That's the tan, right? So it's going to be, and I'm going to write it just to make sure you understand. So it's B prime divided by AB. It's just pure trigonometry. And then we remember that B prime is delta, right? So B prime is delta. So it's a little delta divided by AB. Delta we calculated, but we already also know that tan theta, because theta is small, that the tan theta is equal to theta. And do we know what theta is? Yes, we do. It is pi over 2,000 radians. Okay? And so now, what you need to take into account, I'm going to maybe use a green so this sticks out, is that we have this is equal to that. All right? And from that, we get what? And delta is this. And from that, we just a simple calculation that AB, which is what we were supposed to find, is equal to delta over pi over 2,000. And when you sort that out, so this is 5 to the 10 is equal to 5 times 10 to the minus 5 meters. And this is in radians, so we basically just lose them. Divided by pi over 2,000, that means divide by pi and times 2,000, right? And from there, AB ends up being 3.18 times 10 to the minus 2 meters. And from that, we see that AB is simply 3.18 centimeters. It makes sense, right? So the length of this has to be 3.18 centimeters. The length of this bar was 50 millimeters. That's 5 centimeters. So it was a pretty decent picture I drew. I didn't draw it on scale, to scale, but it seems it's pretty close to scale. Okay? So that's how you solve this problem. There's no higher thinking. We did all this in class. You had a simple, I didn't give you any weird stuff that you have to figure out weird trigonometry. It cannot be simpler than that. Okay, so again, I don't know why it didn't go. All right, so that's this problem. Now we are going to solve the key problem that I really thought it was a gimme, but it turned out not being a gimme. Okay, let me read it first, and then we'll see what it is. The assembly has dimensions and properties as indicated on the picture. Determine the reactions at the wall when it's loaded as shown. So we have everything in 1s, 2s, and 3s. Okay, the aluminum is E over 3. E is we're comparing them all with steel. So the steel has the smallest diameter, modulus E, and the length L. Then the bronze part in the middle has the half the modulus of steel, twice the diameter of steel, and twice the length. And aluminum, a third of the modulus, 3 times the diameter, and 3 times the length. It's a pretty cool problem, okay? And anyone having their head screwed on right will know that there's something simple coming out of this, right? Because a lot of stuff will cancel out. So let's start working on it. The first thing that we need to understand is what happens with this body. We have a statically indeterminate problem, which means we have, maybe I can make this slightly smaller so that I can fit more on the page. Let me just do that. Okay. Sorry, I'm getting there. Oh, that's the one. To give it as much space as possible. Okay, maybe a little bigger. Whoops. There you go. So we need to determine the reactions at the wall. And we have both walls. and it's stuck in there. So because you know you have three support reactions in this end and three support reactions in that end, or even if you discount the fact that there is no, even if you count on the fact there's no vertical forces, just axial, you have a force and a moment here and a force and a moment here, and it's no good. So you have too many unknowns, and how many equations do you have? Just one for the axials, but you have two unknown reactions. Forget about the moments too, because we don't have any vertical forces. So two reactions, one horizontal reaction in the D and one horizontal reaction in A, and you only have one equation, sum of axial forces. So clearly you have a statically indeterminate system. So what do we do when we have that case? First thing first, we immediately draw these lines, and actually I'm going to look at the thickness of my lines and do very thin, and then I'll use thicker for other stuff. It's weird drawing on this writing pad, but I guess it's okay. All right, so we have that. And what is our first thing? And let me choose a little thicker pen and maybe a red pen and a little thicker. Okay. And so what do we need to recognize? The way we solve statically indeterminate problems is to divide it into two problems by using a principle of superposition. We're going to superimpose, add up two different problems, okay, that are both very simple, much simpler than the problem we are having here. And one of these both of them will have the wall removed. And so let's say this is going to be equal to what? The first problem is I'm going to remove this wall here. Okay, so let's remove that wall. And when you remove this wall, this problem is equivalent to two cases. The first case is this case. Remember that due to these forces, there is some sort of loading it will happen. The wall prevents it from moving. But as soon as you remove the wall, it will, imagine it's made of rubber. What's going to happen to it as soon as you stop holding it at this end? The forces are pushing this way, so it's going to shrink to the left, right? So just draw that. This is the logical outcome of removing that wall. Okay, and so that's your case. And there's the wall. This is your first case. And that first case actually has all the original forces that are external forces, right? And what we do, we know that because of these forces, there is no wall, the whole bar deformed and sort of creeped to the left. And so we know how to calculate, let me get it very thin. We know how to calculate this amount here. And notice how you're supposed to do this, because you didn't do it and you got confused. A lot of you who actually managed to figure something out, you got confused because you need to actually write the little arrow. And this tells you that this is delta, the deformation of this, axial deformation of this bar, due just to external forces F, delta F, okay? And then, so that's the first case. And then plus the second case, where we draw the same bar, now returned to the wall. This is the key bit. And still the left wall is there. It has not gone anywhere. We have not ignored it. We just got rid of the right wall. And I'm going to use the violet. All the external loads are gone now because you're adding two cases. The first case would be just the external loads, no wall. The second case would be no external forces, but the reaction of the wall. Because remember, the wall pulled it back. And I'm going to call this RD because it's the reaction of the wall in the point D. And so what happened, you draw this to understand. You draw it, it was here, okay? But now, I forgot to make it very thin again. Now it went from that position back to the wall, okay? And that's delta R. So to summarize, this problem that is statically indeterminate because it's tied to two walls is equivalent to the sum of two cases, the effects of two cases. The first case is the bar without the wall, the right-hand side wall, with all the external loads, which are these two F's. And the second case, the bar with no external loads and just the reaction of the right wall that brings it back to the wall. And so what you see happens here is exactly this, that delta F is equal to delta R. This is your condition of compatibility that it makes this solution possible. It basically says that whatever forces, external forces do to the bar, the wall does it back. Okay? So whatever deformation the forces cause, the wall undeforms it back. And so all you have to do now is calculate this for two different cases, right? And so we're going to do that step by step. So first, and I'm going to use now a different pen, maybe dark green. Okay. So first we have to solve this problem, and then we have to solve that problem. And hopefully I will have enough room, but look how I'm going to do it, okay? So first I'm saying, I'm going to now try to write this delta F, okay? What is it equal to? And I'm going to be writing it in the one line because I know where it's going, but I will tell you how I got these things. Delta F is really, this is the deformation of the whole bar. This is point A, this is point B, and this is point C, and this is point D. So that's really equal to delta, the difference, the elongation or the shrinking of the point D with the respect to point A. And so how do we calculate that? And I'm going to go and do that here. So the first what we're going to do, we're going to start from left or from right to count these deltas, right? It's going to be some sort of sum of what? The formula that everybody kind of gets. The normal internal force, not external, internal, times the length of the section and divided by what? By E of the section, the modulus, times area of the cross section at that section. So how many different sections do we have? 3. So this will have to have 3 different things, okay? So let's cut the first one. And I'm going to now be writing this as a delta F, right? Let me write a little lower. So delta F is equal to what? The first section I'm going to cut here, and I'm going from the right to left. So if I'm going from the right to left, do I see any forces here? No. So actually, that first displacement of point D with respect to this point on that in this section I made here is 0. So I'm ignoring it. The next section I make is this one. So now what do I have? I have something that looks like this. I just have this stump, and I'm going to highlight it in green, okay? And this force here. So all I have is the green stuff now, no red stuff anymore. And in this green stuff, I have the green force here, and so the reaction from this green F, that's the external one, will be this guy here. And that's also going to be equal to F. So although I could just write these independent diagrams here, or one under the other, there's not even need to do that. A lot of you have solved this thinking that that's the solution for the whole problem, and then you didn't really know what to do with here and sort of collapse right there. But that's just the solution to this part. The solution to this part was not addressed by most of you. Okay, so then this would be equal to, what is the normal force in that section? It's F, right? Because all we have is these two. So the internal load ends up being F times, what is the length of that section in which we are parked? It's 2L, so it's 2L divided by, what is the E in that section? It's E over 2. And times, what is the area? The area is 2D divided by 2, right? So that's just D. And then the whole thing squared, so I'm going to write it. 2D divided by 2 squared times pi. Okay? And that's the end of it. That's it. And so now the next one, plus. So now we're traveling. We keep traveling. So what I'm going to do now is, you forget this green stuff. So now I'm going to use a different color. I'm going to use maybe violet. Okay? So I'm making a violet cross section. And now the beam that I'm looking at is this violet part. It includes the part of the green, right? Up to here. These other sections don't exist now. So now I have the violet beam that has two F's, one here and one there. I have to have some water. And we are looking now, we have two loads, the F here and F there, and the cross section here. Okay? And if you look at the free body diagram of this, just for that cross section for everything on the right, you will have a resultant force that's also pointing into the section that's equal to the sum of these two, which is 2F. Okay? Please don't do this in the exam. I'm only doing it on top of each other because I'm not doing it in the classroom, and I don't have enough room to do all that on the screen. Okay? I'm not that good with this pen. So this is only because I'm in this situation, not because I want you to have all these things drawn on top of each other like this on the exam. That's not allowed. Okay? That's why I'm using different pens. So 2F is the internal force in this last section. And so now the displacement there would be equal to the internal force, normal force, which is 2F. So I write 2F times L. The L is what? 3L. Okay, times 3L. So this is just for that section. Okay, divided by the modulus for that section, which is E over 3. Times the area for that section, which is 3D half, that's the radius, 3D half, and then square times pi. And that's our delta F. And so if we calculate our delta F, and now I'm going to go crazy and use an orange, and I'll just show you what the final result for delta F is. It is equal to 12 FL over pi E d square. I notice that a lot of you don't know what to do with numbers and immediately start dividing by pi. In engineering, this is a result that you want to show. The pi is a number you can use, but this is how you show the results when you're solving your equations. You never divide with pi until you're ready to find some real numbers. So this is our delta F. And now we have to calculate the delta RD. Okay, so delta RD, that's for this case. So now I'm going to switch back to the violet and see what the delta RD is equal to. Okay, so that's the displacement, this guy, delta R is equal to really delta of the point D with respect to point A. Again, the same, but due to R force. So this is D with respect to A due to R. And the other one we did up there is delta of D due with respect to A, but due to F. So you see these two are different. But they're both displacements of this point D with respect to A, the total, okay? And I said I was going to use violet. All right. And so that is equal to what? And now we're going to have several terms there. Because now we have three different sections and we just have this one loading. So for each section, as we're calculating the effect of this loading, for each of these sections, we will have just the same force. The reaction here for this part would be RD. The reaction would be pointing out, and it would be equal to RD. If we cut the section here and look at the reaction there, again it will be pointing out, again it will be equal to RD. So for all these three sections, the reaction is RD. So how do we calculate when we do that? It's very simple. You just go one by one. Apply this formula for each section with RD where N is. And so you get this. You get the first one is N, okay, so it's RD times L. The L on the first is L divided by E, and E for the first part, the steel, is E, times the area, which is D square pi over 2. So this would be D over 2 square times pi plus, and I'm just going to write it all in one line, actually, a little further down, plus. So we've finished with the first section. Second section, same thing. The force is again RD. The length is this time 2L. The E is E over 2. And the area is, the D is 2D. And I'm going to write it like this so that we don't lose it. 2D over 2, right? Square times pi. And plus the last section is RD again times the length is 3L and the E is E over 3 and the D is 3D. So the area would be 3D over 2 square pi. And guess what happens when you calculate that? You get the delta, whoops, look what I've done. You get that delta R is equal to 12 RD L over P, or pi as you like to call it, ED square. Now lo and behold, what happened here is the same as this one. Well, if you kind of have done a few of these problems, you kind of guessed that from the geometry, right? That's how I chose your geometry. And so you got them that they're the same. And so what I'm going to do now, we haven't even gotten to this wall, the other wall, the left wall, but we were asked to calculate the reactions at the walls, right? The both sides. And so how are we going to do it? Remember these two numbers. I need a little more space, so I'm going to introduce a new page, okay? And I'm going to draw the diagram, which looks like this. I'm going to not spend time drawing, but I'm going to pretend that I got rid of these two walls. And now I'm going to just have two forces, okay, that are reactions. This is RA. This is a new diagram. And this is RD. And you have copied those two solutions for delta R and delta F, and we said that delta R is equal to delta F. And so we set the 12 RD L over pi ED square is equal to the same thing, 12 FL pi ED square. And from there, what we see, for some inexplicable reason, the single person that was actually able to come this far could not understand, was confused here. And I don't see the confusion. The only thing I see here is I don't have to use even the modicum, even the smallest amount of calculation. I can see from here that this guy is equal to that guy. Now you may be thinking, well, it's obvious, but I'm sorry, it's not obvious. You got to solve it. So RD is equal to F. And so what is our diagram? This is our diagram. The free body diagram for the whole body without the walls, with just the supports. And it looks like this. This is RD. This is RA. Okay? And the forces are this and that. This is F and that's F. And we see that from sum of x's equals to 0, we see that RA minus 2F minus F minus F minus RD is equal to 0. So from there we see that RA is equal to RD plus 2F. Right? Oops, what did I do wrong? Yeah, I did this wrong. This is not it. Okay, wrong direction, because I assumed that, remember, it was going in that direction. And I shouldn't be changing my mind halfway through the problem, right? We said it's in that direction, it stays in that direction. So then here it's the plus. And so here we get this, that RA is then equal to 2F minus RD. And it's equal to 2F minus F. And from there we see that RA is also equal to F. So this is our solution. I knew you would hate me because all this work to get something so simple, but that's how life usually is, okay? So both reactions are simply F. If I had not applied F here, if I had done a different number setup, it would not be that simple. But it took me about an hour to get these numbers just right so that you get such a beautiful, simple result. So no calculators were needed in this one, all right? It's one of the simplest problems you could get for statically indeterminate problems. All right, and so the last problem is this one, which I again thought was a gimme, but oh my God, was I wrong. Apparently it wasn't a gimme, and so now I have to work on it with you. What do we have here? We have the turbine that outputs power P. A lot of you really had the problem with using the letters instead of numbers. It baffles me. Because as engineers, you better be used to generalizing like that. You can't just be solving, knowing how to solve 2 times 3, but you don't know how to solve 27 times 58. That's a problem. So in general numbers, the turbine outputs power P. Another big problem I had that I noticed is that a lot of people, for some inexplicable reason, got confused with this symbol here. That means the power P with the units of watts. I purposely told you what the units are because I didn't want you to do, if you do conversion, I want you to do conversion. But if you don't do conversion, I don't want you to do it. So I organized the whole problem so that you do not focus on conversion at all. So the diameter is in meters, the D, shear modulus G is in Pascal, so everything is in European units, okay? And angular velocity W at the journal bearing right here somewhere. And so it allows the shaft to turn freely about its axis. And what you need to understand is the first part is, what does it mean that the power is transmitted to the gears in such a way that B and C receive an equal amount? That means you have something else on this gear, but it doesn't matter to us. It means that whatever is passed there is half of this power that is output by this. And the same here, okay? And so that's the first information. And what you need to find is the absolute maximum shear stress in the shaft and the angle of twist, D, which is here, relative to A, which is right here. So the angle of twist of this point with respect to that point, okay, due to these losses of power. Imagine that there are other gears there and they're obstructing it. So because there's a load there, right, when it obstructs, there is action and reaction. So half the load is here and half the load there. What are the loads? Torques. So what you need to see is that although I've given you the power, you immediately have to figure out what those two torques are. And that's your external load. And then you forget about the power, okay? And so you need to draw the diagram for that. And once you sorted all that out, then you can start calculating the shear. I was amazed that people directly jumped into the shear and started plugging and chugging into the shear formula without even looking at what are the loads here, without sorting out what is my load. Is it a force? Is it a power? What is it? It's a torque. So we're going to go step by step, okay? Let's do it. And let's move this up a little so that I give myself plenty of space. All right. So what do we have here? There is no reason for you to draw a sideways diagram when you can draw a proper diagram. So I'm going to draw a proper diagram now, and I'm going to use a thick one for the shaft, and I'm going to do it here with, let's say, a green one. And here is my shaft. That's my shaft, okay? And there is a P here, but I don't even care about it, okay? What I have is the shaft. And we're just looking into torques, okay? So now I'm going to draw. I'm going to use blue, and I'm going to use a thin one. And what do we have? We have at L and 2L. So this whole thing is 3.5 L long. See, L plus 2L plus 0.5. Does this part here do anything? We'll see. It doesn't. There's nothing. We said it's a bearing that just holds it, but it doesn't really take any torque. It doesn't obstruct the torsion, the twist. Okay. So I'm going to draw around these 2 points, this one and let's say that one. Okay. The lengths are not drawn to scale. I'm going to draw torques. So this is the first one, right? Because it's rotating in that direction. It really doesn't matter how you draw it, but you have to understand that both of these are in the same direction. That's all there is to it, okay? And then, if these are in that direction, I'm going to use a red one to make sure you understand. This is the one right there in the opposite direction. So that's the reaction. That's what's here. And these are the two guys that it outputs, right? So these two guys, this red guy gets lost or spent on the two blue guys. And so now let's do some marking here. I'm going to use a blue pen and I'm going to make it really thin and start writing something. So what do we know about the power? And I'm going to call this, this is a point C, and this point is B, and this point is A. Okay. And what I know is, I will write it here, is that the power at B is equal to the power at C. It says it gets spent equally on these two. And that means that each of them is a half of the P. So that was the simplest thing you should have seen, and the simplest thing you should have written first right away. And we know what a torque is. If we have power, we know what a torque is. So the torque is then equal to, the torque is normally equal to, I'll write it right here, or maybe right here. Torque is usually equal to P over 2 curly W. Okay, that's the angular velocity. And so you have both of these. So that means you have the T. So your TB is equal to TC is equal to P over 2. Will be used instead of P. So it's equal to P over 2 over 2 omega. That means each of these two guys is equal to what? And I made a mistake here. I have to correct because I'm thinking ahead. There's no 2 here. Sorry about that, guys. The torque is just P over omega. Okay? There you go. So the torque is power over the angular velocity. Our power is P over 2. So it's P over 2 omega. So that each torque is P over 2 omega. And so now that we know that, now we have to draw here, this guy here is TC, and this guy here is TB, and that's the value, okay? And so let's draw the diagram. The distribution of torques along this shaft. Okay. Nice. I'm beginning to enjoy this. Okay, and so how are we going to draw it? Well, first we said we need to draw the dimensions because we mustn't forget. Okay, and so this is 0.5 L, this is 2L, and this is L. And so it's very easy to draw the torque. It's clear what it is. The torque here, I'm going to use a thicker pen. The torque here at this point is this red guy, okay? So that's equal to P over omega. Then no changes until it hits this torque. So that's a thicker one, okay? And then it drops down by half, right? Because that's the TB. And then no changes all the way up to this other guy. So I'm going to draw this a little thicker. So this is P over 2 omega, right? And this is P over omega. So these values here. And this value is P over 2 omega. And then at this point, it loses another half. So that means it hits 0. So there is no torque in the part from here to there because we already knew that all the power that you put in gets spent right there and there, the equal amount. So there's nothing here, no torque. So this part stays undeformed. If you drew a straight line, it would stay straight. It would be turning around with everything else, but the lines here would be going around like what we saw in the lab. Okay, so this is P over 2 omega. That's your diagram of internal torques. These are external torques, okay? And so now what do we have to see? We have to see at where is our maximum torque here? Maximum internal one. And we're going to use that one to calculate the absolute maximum shear stress in the shaft. Well, it's clear that the maximum is in this intersection. So right there, our torque maximum is equal to P over omega, okay? And that's at this part of the shaft BA, okay? At that first section here. All right, and so now it's easy to calculate the tau, and let's do it. The tau maximum will be equal to what? We know the torsion formula. It will be, because I put the max here, I'm going to put the max here, but normally it doesn't really have any subscript. It will be equal to T max, the torque, the maximum torque, times the c, the maximum diameter, over j, okay, the angular moment of inertia. And the angular moment of inertia for this shaft, which is of diameter d, is equal to pi over 2 c to the fourth power. Our c is equal to d over 2. So let's just substitute that, and we're going to have that equal to, I'm not going to substitute the d actually yet because I don't need it just yet. It will be equal to here, instead of j, we'll have a c to the fourth power. So let's substitute that. It's going to be equal to p over omega, okay, times c over pi over 2 times c to the fourth power. And now the c and the fourth power cancel, and you get the c to the third. And that's equal to, when you sort it out, you get this value, 16p over pi omega d to the third power, right? Where instead of c to the third power, we wrote d half to the third power. And that's your solution. That's your tau max. Expressed in terms of known quantities, the power, the angular velocity, and the diameter, okay? So that's the answer to the first question. That was A. And now we're going to do B, and then we're done, okay? So B was the angle of twist of D relative to A. So that's fairly simple. We are going to start with writing this, the phi of D with respect to A is equal to, and now again we go section by section. We're going to start at here. All we have to look, we don't have to look at the shaft anymore, we just look at this diagram, right? So the first cross section is here. What is the value of the torque here? 0. So, and we know that all of them, let's just write what the formula is. The formula is for the twist angle, it is equal to the torque times the L, the length of the shaft, divided by JG, where G is the shear modulus, which we have, and J is the angular momentum. So all we will have changing along this shaft, the J and G stay the same, L is changing from section to section, and T is changing. So let's just take 1 over JG out, because we know we'll be adding all these things. Whoops. And go section by section. So in first section, there is no torque, so it's 0. So torque, 0 times everything else is 0. Then we have plus, and all we have to keep doing is T times L, the sum of T times L. So the torque for this section, the second section, is P over 2 omega times the length for that middle section is 2L. 2L. That's it. And then the third section, this red section here, again plus, the red section, the torque is P over omega times the length of that section, which is just L, okay? And that's the end of it. And when you calculate that, it's equal to 2P L over 2J omega. And the only thing that remains is to substitute instead of, sorry, I keep saying 2 when it's J. The only thing that remains to substitute is the j, right? Which is this here. Instead of c, you write d over 2. And you get the final result that phi or phi of d with respect to a is equal to 64 pl pi g omega d to the 4th power. And that's your solution. Okay? And that's the end of this exam. It was very easy, but some people really had a hard time with it. Okay? All right, good luck on the next one.